Hello, I welcome you all. The problem is coming from the Engineering Mechanics and Dynamics 14th edition by RC Hibbeler. We have a problem where we have a barrier which is placed in front of the bridge pier. And we've been given a function that relates the force and the deflection of the barrier. We have been asked to determine the maximum penetration of the car in the barrier. Okay, and we've been given the weight of the car, which is 400 pounds, and its traveling speed just before it hits the barrier, which is 75 feet per second. Right, so let's start with drawing the free body diagram. So we do have the weight of the car, and we do have the normal reaction. This is W equal to mg. Let's call this NA. Let's call this NB. Right. So the velocity of the car just before it hits the barrier is 75 feet per second. The maximum penetration, so let me write here. So the maximum penetration in the barrier will take place when V final or V2 is equal to 0. Okay, and then so immediately the car hits this barrier, there will be a reaction force from the barrier to the car, right? And that reaction force will have this magnitude of force, which is given, that relates the force to the deflection of this barrier. So we'll have a reaction force. Immediately the car hits this barrier, and this is F. Okay, so we have this point here. Let's say this is the point where the car comes to a stop. So let's write down this information here. So we have V1 here, which is equal to 75 feet per second, and we have S1, which is equal to S0, and is equal to at this point it is equal to 0. Then we have V2, which is supposed to be equal to 0. By this time the barrier will have been deformed and the car will have come to a stop, and the question is to determine the length of deformation, okay, or the depth of deformation. Okay, so S here, S2 is just equal to X, right? Okay, then a few pointers here. The displacement. So here we want to use the concept of work and energy. We are still able to solve this particular problem by just using the equations of motion, but we are in chapter 14 where we are using work and energy. And using this particular concept, we'll be able to work out this particular problem and find this penetration depth. But let's take note that the displacement for W, normal force NA and normal force NB will all be equal to 0. Okay, and therefore UW is going to be equal to 0, UNA is going to be equal to 0, and UNB will be equal to 0. Okay, so what does this concept of, and this U is the total work. Total work due to weight, total work due to normal force at A, and this is the work due to the weight is going to be equal to 0. The work due to the normal force at A is going to be equal to 0, and the work due to the normal force at B is going to be equal to 0. This principle of work and energy states that the kinetic energy, the initial kinetic energy in the system for a particular system, so the kinetic energy, the initial kinetic energy plus the total work from point 1 to point 2 is equal to the final kinetic energy. So the initial kinetic energy of this vehicle is half mv1 squared, and this is equal to half. Our mass is 4,000 divided by 32.2 times 75 squared. And KE1 is just going to be equal to 0.5 by 4,000 divided by 32.2 by 75 squared. And this we get a 34.9378.882. And then KE2, which is the final kinetic energy, is equal to half mv2 squared, but our v2 is equal to 0. Therefore, all this goes to 0, and our KE2 is just equal to 0. Alright, and then our summation of the total work from point 1 to point 2 is just going to be equal to, then let's look at the direction. When the force and the displacement, if they are in the same direction, we have positive work. When the force and the displacement are in the opposite direction, we have negative work. So what is the direction of our work here on this particular car? Of course, it is going to be negative because the force F is in this direction and the displacement is in this direction, right? So this is going to give us what? Negative work. Alright. So here I'll say minus integral from S1, S2, then F ds. And our S1 is just equal to S0, which is equal to 0. Our S2 is just equal to X. Our F is already given to us, is 90,000 X to the power 0.5. And our ds, since we'll be integrating with respect to x, this becomes our function is with respect to x, this becomes our ds. Therefore, the total work is just equal to minus from 0 to x, 90,000 x to the power 0.5 dx. Okay, So this is just equal to minus, this just becomes 90,000 divided by 1.5 x to the power 1.5, right? So with this, then we can simply say, let's plug this into our equation. So we do have this equation, kinetic energy initial plus total work equal to the final kinetic energy. And the initial, we found that this is equal to 34,9378.882 minus 90,000 divided by 1.5 x to the power 1.5, and this is equal to 0. Making x subject of the formula, which we can do. So I have this, I take it the other side there, so times 1.5 divided by 90,000. Okay, so you can do this. This just becomes 1.5 by 34,9378.882 and divided by 90,000, and then you can just do this by 1 divided by 1.5, and also this side by 1 divided 1.5. Therefore our x is just going to be equal to 1.5 by 34,9378.882, okay, divided by 90,000 to the power 1 divided by 1.5, 1 divided by 1.5. Right. So our x is 3.24 feet. So this is the deformation in the barrier, and this is the displacement, how much the car will have moved as it hits the barrier. It will move from this point, it will move 3.24 feet. That's what we are saying. Okay, so this distance here, if I was to show this, what we are saying is from this point going in this direction, this value here is equal to 3.24 feet. That's what we are saying. I think this is about it. We found the maximum penetration length, okay, into the barrier, okay, into the barrier once the car hits this particular barrier. So I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, subscribe, and continue sharing. You are able to solve this particular problem by using the equations of motion. Bye bye, and I'll see you in my next screencast.